Olá a todos, bom dia. O próximo evento vai ser o primeiro evento em inglês dessa semana, então a partir de agora eu só vou falar em inglês. Now in English, good morning everyone. Our next guest is going to be our first international guest, Professor Nisarg Shah, who is an assistant professor in the Department of Computer Science of the University of Toronto. His research lies at the broad intersection of computer science and economics. Shah is interested in the issues of elicitation, aggregation, fairness, and incentives that arise for interaction of multiple agents. His recent research has focused on fairness, exploring what it means, and designing provably fair algorithms for different settings. Shah received his PhD from Carnegie Mellon University and was a postdoctoral researcher at Harvard University. He's also the winner of many awards such as the 2013-2014 Hyman Jive Graduate Fellowship, 2014 and 2015 Facebook Fellowship, and 2016 Victor Lessa Distinguished Dissertation Award. Please, Nisarg.
All right. Thanks, Rodrigo, and thanks all the organizers for organizing this wonderful event. I'm very happy to be here. Let me share the presentation. So I hope you can all see the slides. All right. Okay, so the topic of my today's talk is going to be pushing the limits of fairness in resource allocation. And because we have such a broad and wonderful audience here, covering everything from undergraduate students to professors, I'm going to keep the talk at a bit high level. I'm not going to dive too deep into any of the details. But know that all of the stuff that I'm going to mention, these are things that you can rigorously prove in a very mathematical fashion. Okay? But just in the interest of the broad audience, I'm going to keep the talk at a high level, and I'm going to talk more about what the field of fair division is and what kind of things it looks at, and how do we define fairness formally when we are allocating resources to different individuals. So, as you all know, algorithms are pretty ubiquitous in today's world, and there are more and more domains where these algorithms are starting to make real-world decisions. So everything from who gets loan or who gets out on bail, or how a self-driving car drives, to what kind of ads you see when you search something on Google. All of these things are decided by algorithms, even filtering resumes when you apply for jobs, or whose organs are implanted into whom. So these are really high-stakes decisions that affect real human beings. And sometimes when these algorithms make a decision, it affects not only one human, but several different humans. And these different humans may have different preferences, often conflicting preferences, over what they would want the decision to be. And when that happens, the algorithms obviously need to find a consensus or trade-off between these conflicting preferences of the different humans to arrive at a decision. And that is what this field of computational social choice focuses on. It looks at algorithms for aggregating individual preferences towards some collective decisions. And making good decisions is a multifaceted issue that involves various aspects of the problem. So you have to question whether this decision is ethical. You have to question whether it is fair to the different participants in the system. You have to look at how you are going to elicit the preferences of the different participants, how you are going to ask them what they want. You also have to wonder about whether the decision is efficient in some sense, and we are going to make many of these definitions clear throughout the talk. And finally, you also have to think about what kind of incentives your system provides to the participants. So once you design the system, do the participants have an incentive to behave badly or in an unexpected way? So these are the different aspects that you need to think about when you define what a good decision means. And today I'm going to focus on just 3 of these aspects. I'm going to focus on fairness, which is going to be the key focus of the talk. But I'm also going to talk about efficiency and incentives. And I'm going to initially just talk about fairness and efficiency, and I'm going to keep the discussion of incentives until the very end of the talk. Right. And I'm going to focus on all of these in the context of resource allocation, which, as I said, is just the problem of allocating a bunch of resources to a bunch of individuals. And these individuals have different preferences on what resources they want to receive, and the question is, how do you want to allocate these resources in a fair manner? And this problem has a variety of real-world application. So, for example, the classic application is inheritance or estate division. So when someone dies and they leave behind an estate, this estate needs to be divided between the different heirs, and these heirs might have different preferences on what part of the estate they want to receive. Another classic application is divorce settlement. You can also just think of a group of friends who collectively bought something and now want to divide it amongst themselves. So, for example, one of the real-world applications that I came across is there were some group of friends who bought a season pass for a football game in one season, and now they wanted to divide the tickets to the individual games of the season amongst themselves. And to help people deal with these kind of problems in the real world, my collaborators and I, back in 2014, we started this website, not-for-profit website, splitit.org. And our goal in designing Splitit was very simple. We just wanted to take some provably fair solutions that were already known in the literature for a bunch of different problems, and we wanted to make them available through this online platform for people to use freely. Okay, and so if you haven't tried Splitit before, I highly encourage you to go and try it, because there are many of these problems that even you might have a use for. So, for example, just to briefly go over some of the applications that Splitit offers, one application is share rent. So this is the thing that you use when you are a bunch of roommates living together and you want to decide who should get which room and how much rent, how much share of the rent they should pay in a fair manner. The split fare application, it allows you to split the fare of a taxi when you take the taxi together, but then you drop off at different locations. The assigned credit applications allows you to kind of split 100% of the credit between the different group members when you work in a group and when you do some joint project. But the focus of today's work is going to be this divide goods application. This is the application which is about allocating resources to individuals. Right. And once we deployed this website, the solution that we had for the divide goods application back in 2014 wasn't a very compelling one. And this was reflected in the fact that after we launched this website, within the next year, we started receiving a bunch of complaints about the allocation procedure that was deployed for this divide goods application. And this user feedbacks, they pointed out various issues in this algorithm. And one of the emails really caught our attention. So this is an email from one of the four brothers who wanted to divide an inheritance of, say, some 30 plus furniture items. And before using Splitit for real, one of the brothers wanted to just try it out on some random, some handcrafted instances and just to see how Splitit works. And on some of the instances, the allocation that was given wasn't quite matching his expectations. So he went ahead and created a so-called minimum working example for us. So in his example, he said, imagine that there are 5 candies. These are identical candies that you want to divide between 3 people. So what can you do? Well, if we had 6 candies, we could give 2 candies to each person, and that would be completely fair. But since we have only 5 candies, all we can do is give 2 candies to 2 of the people, and then the last person is going to get a single candy. It's a bit unfair, but that's all we can do if we have only 5 candies to divide between 3 people. Unlike his expectation, the allocation that was returned by Splitit was something like this, where the one person got 3 of the candies and the other 2 people were left with a single candy each. And this was obviously quite unfair, and even we were troubled by this, so we dove deeper into what the issue is. And before I explain what the issue is, let me just briefly describe what model we are considering. And so in this model, this is a very simple model where we just have a bunch of indivisible goods. So these goods are indivisible in the sense that you cannot split the good into 2 pieces or more pieces and give the different parts to different people. Okay, you have to take the good as a whole and you have to give it to one of the individuals. And here on the other axis, we have the individuals. And each individual has a value for each item. And these values are going to be additive in the sense that, for example, if you take the boy and you give him both the painting and the car, then his value for the 2 items combined is going to be 67 plus 150. Okay, so the values sum across the different goods that you receive. formally, you have a set of n agents, you have a set of m indivisible goods, and then each agent, his preferences are explained by this valuation function vi, which assigns a value to every subset of the goods that the agent might receive. Okay, so for every bundle of the goods that you might receive, you have a value. And as I said, the values are additive. So the value of a bundle of goods is just the sum of the values that you have for the individual goods in the bundle. And an allocation is simply you take all the goods and you partition it into n bundles, and you give bundle 1 to agent 1, you give bundle 2 to agent 2, and so on. And then the utility to agent I is simply the value that agent I places on her own bundle that she receives. And we somehow want this allocation to be fair. So what does fairness mean? There is a gold standard notion of fairness that has been studied in this literature for a long time. And this notion says, is called envy freeness. It says something very simple. It says that once you do this allocation, no individual should look at another individual and envy them for what they have received. Okay, so if you take any pair of individuals I and j, and you look at the value that agent I places on her own bundle, AI, it should be at least as much as the value that agent I places on the bundle given to agent J. Note that we are comparing the bundles of agents I and J by the valuation function of only agent I. Obviously, this holds for all pairs of agents. So even if you look at everything from agent J's perspective, agent J also shouldn't envy agent I. So agent J's value for her own bundle should be at least as much as agent J's value for agent I's bundle, vice versa. So if we can achieve this fairness notion, that would be perfect, because everyone would think that I don't envy anyone else in the system, which means that the bundle that I receive it is at least as good as the bundle that anybody else received, which means I got the best cut of the whole share. But of course, envy freeness is impossible to guarantee when you have goods that are not divisible. Right? And to see this very easily, just imagine that you have one good and you have two people who want this good. You have to take this good and allocate it to one of the two people, and the person who doesn't get the good is going to envy the other person who gets the good. Now, because this notion is impossible to guarantee, the old mechanism that we had on split it relied on a hierarchy of weak relaxations, and the weakest relaxation that it relied on said something like following. In the specific instance where you have five candies and 3 people, it says that, look, we cannot really guarantee that each person should get at least 2 candies because we don't have 6 candies to give out. So let's just make sure that each person has at least 1 candy, and subject to that, let's maximize the total value that all the participants have in the system. Let's maximize the total happiness. Now, the problem with that is that once you give 1 candy to each people, so you allocate the first 3 candies, giving 1 to each, for the remaining 2 candies, it doesn't really matter who you give them to, because no matter who gets these 2 candies, they are going to derive the same value out of these 2 candies. Okay, so if your goal is to just maximize the total happiness subject to each person receiving at least 1 candy, you can just take the remaining 2 candies and give it to the same person. Okay, and that person would now receive 3 candies, which is obviously quite unfair. So to resolve this issue, we look for some stronger relaxations of envy freeness. And the relaxation that we found compelling in the literature is called envy freeness up to 1 good. And what this says is that, look, we cannot really prevent agents from envying other agents when we divide goods, because these goods are not splittable, not divisible. But at least if agent I envies some other agent J, we can limit how much this envy is. And the way that this axiom places a limit is it says that there should be some good that is given to agent J, such that if you ignore this good for a moment, then agent I wouldn't envy the rest of the goods that are given to agent J. Okay, so formally, if you look at any pair of agents I and J, then there should be some good in the bundle allocated to agent J, such that the value that agent I places on her own allocation, which is the utility that she derives from this allocation, should be at least as much as the value that she has for agent J's allocation minus this 1 good. Okay, so if I remove some good from J's bundle, that should be enough to eliminate the envy. So the envy is somehow limited to this 1 good in agent J's bundle. So this is great because in the previous instance that I mentioned about 5 candies and 3 people, it would eliminate this bad allocation where a single person gets 3 candies while another person has just 1 candy. Because if that happens, that would not be envy-free up to 1 good. The person who gets 1 candy would continue envying the person who gets 3 candies, even if you hide one of the candies from their bundle. So this is a strong enough notion to prevent that kind of bad instance. And in fact, it turns out that you can achieve this notion very easily. You can just run a simple round-robin procedure to get this envy-freeness up to 1 good. So let me show you how this round-robin procedure works. So say you have all these paintings to be divided between 3 people, a blue agent, an orange agent, and a green agent. What you do is you line these people up in a cyclic fashion. So you have the blue, orange, green, and then again blue, orange, green, and so on. And then the players take turns picking one item at a time. And in that turn, a player is going to look at all the items that are remaining, and out of that, pick the one that she likes the most. Okay, so the blue agent goes first, she picks this painting, the orange agent says, well, among the remaining paintings, this is the one I like the most. Then the green agent goes, and then we again cycle back to the blue agent, the orange, the green, and so on. And we continue this until all the items are allocated. So this is a very simple procedure. Why is this envy-free up to 1 good? For a very simple reason. So let's try and imagine, let's try and look at it from the green agent's perspective. And let's try to argue that the green agent, even though he might envy the blue or the orange agents, he would not envy them up to 1 good in their bundle. And to do this, I'm going to focus on different phases of the allocations, where I'm going to start the first phase at the first time that the green agent picks an item. And then I'm letting the blue agents and the orange agents pick an item in that first phase. Then again, I have the green, blue, orange, green, blue, orange. So I'm just ignoring the first 2 iterations here, and I'm going to start the first phase from the 3rd iteration. So what do I know about these phases? Well, in each phase, note that the green agent picked an item, and then the blue agent picked an item, and then the orange agent picked an item. So certainly the green agent likes this item at least as much as the other items that are picked in that phase. Because if she liked this item more, then she could have just picked that at her turn. Okay, these items were still available when it was her turn to pick. So within each phase, the green agent doesn't envy the blue or the orange agents for the items that they picked because she likes her item at least as much. And note that this holds for every single phase. And because the values are additive, this also holds across the union of all the phases. So in other words, if you just ignore these first 2 iterations of the mechanism, then the green agent wouldn't have envied the blue or the orange agents. But because agents blue and orange get to pick an item before the green agents, now she might actually envy them, but only up to that 1 good that they each picked before the green agent got her turn. Okay, so if you ignore this 1 item picked by the blue agent and ignore this 1 item picked by the orange agent, then the green agent wouldn't envy them at all, and which is why this simple procedure is going to give you envy-freeness up to 1 good. Okay, so this is great. You have this very nice axiom, envy-freeness up to 1 good, that is going to prevent the kind of bad instances that I mentioned earlier. And you have a very simple, very intuitive procedure that gets you this fairness axiom. So what is the problem? The problem is that this allocation procedure is not very efficient. And here I'm going to use a very classic notion of efficiency in economics called Pareto optimality. So Pareto optimality says that once you have allocated the resources, it shouldn't be possible to somehow reallocate the resources in a different way that gives every agent at least as much utility as before. So nobody is less happy than before, and at least 1 agent is strictly happier than before. At least 1 agent gets strictly more utility than she had before. The point is, if you can actually find a different allocation that does this, that gives at least as much utility to every agent and more utility to some agent, then this other allocation is in a sense more efficient. Your original allocation isn't efficient enough. So what we want is that there should be no other allocation that improves upon the current allocation in this sense. And it turns out that round robin actually violates this efficiency axiom in a very stark manner. In particular, it can even construct instances where once the round robin allocation is complete, you can reallocate the resources in a way that everybody is more happy than before. So the question that my collaborators and I asked back in 2016 is, can we get this fairness axiom, NV fairness up to one good, along with efficiency in terms of Pareto optimality? So does there always exist an allocation that is simultaneously fair and efficient? And we found that the answer is yes. And the our rule relied on this idea of maximizing the NASH welfare, which is this function, which is just the product of the values derived by the different people from their own allocation. And this function is named after the legendary John Nash. So let's look at this through an example. Let's say you have these 3 items and you have these 2 people. And let's say the boy says that his values for the 3 items are 5, 2, and 3. And so that is his valuation. And the girl says that her values for the 3 items are 1, 4, and 5. So that's her valuation. And now you want to try all possible ways of allocating these 3 items to the 2 people to maximize the product of their total values. And it turns out that in this particular instance, the best product that you can get is by giving the house to the boy, which gives him a utility of 5, and give both the painting and the car to the girl, which gives her a total utility of 4 plus 5, which is 9. And then the product of 9 and 5 is 45. And you can check that this is the highest product that you can receive across all possible allocations. Okay, so note that we are taking addition of the values within a player across the different items that they received, and then taking product of the values across the different players. All right. So I'm not going to go into detail of why this particular product rule works so well. That there is a well-founded justification that goes decades back in economics. But I just want to point out one subtlety with using this approach, and that is illustrated by this very simple example. What happens if you have just 2 candies, identical candies, to divide between 3 agents? Say you have fewer candies than the number of agents. So some agent is going to go home with no candy allocated to them, which means that some agent, no matter how you allocate the candies, is going to get 0 value, which means the product of the utilities is always going to be 0 no matter what you do. So in that case, can you just do any arbitrary allocation? Can you just take both the candies and give it to one of the 3 people? Certainly not, because that's going to violate NV fairness up to one good, because the person who gets 0 candies is going to envy the person who gets 2 candies by more than one good. So to go around this subtlety, our rule does something like the following. It says that first you have to find the largest set of agents, the maximum cardinality set of agents S, to whom you can simultaneously give positive utility. And once you do that, you only want to maximize the product of utilities of agents in S. And so in this example above, what you would do is that you would take, you would know that I can only give positive utility to 2 of these 3 agents. So I set S to be the set of 2 of these 3 agents, any 2 of these 3 agents. And then I maximize the product of utilities of only those 2 agents, which is achieved by giving both of these agents a single candy each. And so my collaborators and I, back in 2016, showed that this maximum Nash welfare rule satisfies both the fairness and the efficiency axioms that we want. And in addition to that, we also showed a bunch of other fairness guarantees, but in the interest of time, I'm going to skip that. So we deployed this rule in Split back in 2015, once we finished work on this paper. And since then, we have not received any complaints about unfairness in the allocation procedure. So that's a good sign, indicating that this rule indeed might be outputting fair allocations. Okay, so before I move on to the next part of the talk, I just want to focus on some open questions, because this field is rife with as many open questions as it is rife with compelling results. So one open question concerns computation. Note that I haven't really talked about how you actually compute this maximum Nash welfare allocation, because maximizing Nash welfare involves maximizing the product of the values that the different agents achieve. And maximizing the product is a very difficult objective. And in fact, it is strongly NP hard to compute. So, so the question is, while this maximum Nash welfare rule is strongly NP hard to compute, can you at least compute some other allocation that is both fair and efficient in polynomial time? And this has been one of the most challenging open questions in this field. And there was some recent progress in 2018 by Burman et al., who showed that at least we can get pseudo polynomial time, if not polynomial time. Okay? But this polynomial time question is still open. Another open question surrounds a property of fairness that is stronger than NV freeness up to one good. It is called NV freeness up to any good. So recall that in NV freeness up to one good, we ask that if agent I envies agent J, by ignoring some good in agent J's bundle, this NV should go away. NV freeness up to any good just strengthens this property. It says that if you ignore any good allocated to agent J, any good whatsoever, even the good that agent I has the least value for, that should be enough to eliminate the NV that agent I has for agent J. Okay, so there's just a slight difference in quantifiers. It says that for all agents I and J, and for any good G that is allocated to agent J, ignoring G should be enough to eliminate the NV. And the key open question here is that even if you forget about any efficiency requirement, even if you just think about this fairness notion, does there always exist an allocation that satisfies this fairness notion? So this very simple question is still open. So after 4 years after we proposed this, by the way, so when you have only two people, it is very easy to show that an EFX allocation always exists. But when you have 3 or more people, this question was open for 4 years after we proposed this definition. And just this year, Chaudhary et al. Presented a paper in one of the top conferences in this field, EC, where they showed that an EFX allocation always exists for when you have 3 agents. So they solved this question for n equal to 3 agents, but the question for 4 or more agents is still open. And just solving this question for 3 agents had this paper win the best student paper award in this conference. So this is one of the most challenging questions out there, and resolving this question either positively or negatively would be very important. All right. So what did we look at so far? We looked at an allocation procedure that is both fair and efficient in the sense of satisfying NV freeness up to one good and Pareto optimality. And after we deployed this mechanism on Split, we started wondering whether this allocation procedure is fair enough. Is this notion of NV freeness up to one good, is that good enough? And the answer that we found is no. Even though NV freeness up to one good is a nice individual level fairness notion, it says that no individual envies another individual up to some one good. It is very heavily violated when you look at groups of agents. So what do I mean? Let's look at this very simple example where you have 4 agents. So you have a circle agent who likes only the circle goods. So he has value 1 for the circle goods and 0 for the square goods. And you have the square agent who likes only the square goods. So she has value 1 for the square goods and 0 for the circle goods. And you have these other 2 agents who are more flexible. They like all the goods. They have value 1 for all the goods. And let's say we have 2 circle goods and 2 square goods to allocate. And suppose that we can consider the following allocation where the first 2 agents get nothing and both the flexible agents get a circle and a square good each. So I'm claiming that this allocation is fair at the individual level. It satisfies this EF1 notion. Why? Let's look at the circle agent. Certainly the circle agent envies the flexible agent because the flexible agent has this 1 circle good. But if you ignore this 1 circle good, then the envy goes away because for the circle agent, the square good that this guy has is worthless. So at the individual level, this is envy free up to 1 good. But I'm claiming that if you focus on this group S of these 2 agents, the square and the circle agent, and this group T of 2 agents, which are the 2 flexible agents, then in a sense, group S envies group T by more than 1 good. And what do I mean by that? Well, if group S were to take the resources allocated to group T and divide it amongst themselves, then here is how they would divide it amongst themselves. They would take both the circle goods, give it to the circle agent, and both the square goods and give it to the square agent. So both the circle and the square agent would have received 2 more utility than what they have currently. So even though each individual agent only envies another individual agent by 1 unit, somehow the group S as an aggregate envies the group T as an aggregate by 2 units per agent. So this is a violation of this property. Now, some of you might be thinking at this moment, well, I just defined a stronger guarantee of envy freeness up to any good. And if I just impose envy freeness up to any good, then at the individual level, then this bad problem wouldn't have arisen. Because even though the circle agent doesn't envy the flexible agent if you ignore the circle good, he still continues to envy the flexible agent if you ignore the square good. It turns out that you can also create more complicated examples where this group level violation of up to 1 good fairness remains even if you have envy freeness up to any good at the individual level. So what we next set out to do is to formally define this group level fairness and then design algorithms that satisfy this group level fairness. And just before I dive into the details, why would you care about fairness at the group level? Well, there are several applications where agents naturally have groups where you would care about fairness. So imagine that you are a school district trying to allocate educational resources like textbooks or white blackboards or computer equipment to different individual teachers in the school. Now, certainly you want to be fair at the level of individual teachers, but you also might want to be fair to the teachers in different schools, or teachers of different genders, or teachers of different subjects, or teachers belonging to different grades. And so there are various groups of teachers that you might also want to be fair across, in addition to being just fair across the individual teachers. And there is a lot of research recently in machine learning and in other disciplines of computer science on looking at group level fairness notions. But much of this research assumes that there are only 2 or 3 or a handful of groups of agents. And most importantly, these groups are predefined and specified to your algorithm. So the algorithm knows which groups the agents form. And in some contexts, you may not know the groups of the agents in advance. You might not want to give your fairness guarantees only to certain groups of agents. You might want to give your fairness guarantees to all possible groups of agents. And that is what we set out to do in this work with some collaborators. And we defined this fairness notion that we call group fairness. And at a high level, the notion just requires that there should be no group of individuals S that envies another group of individuals T. So what does it mean for a group to envy another group? Well, we use the kind of intuition that I showed earlier in that example. You let this group S take all the resources that are given to agents in T, and you let them redivide it amongst themselves. And then you ask whether this group S is able to improve upon their current allocation by taking T's resources and redividing them among themselves. And by improvement, I mean this Pareto improvement, where every agent in S is at least as happy as before, and some agent in S is strictly happier than before. So in summary, if group S can take group T's resources, allocate it amongst themselves, and find a Pareto improvement, then we can say that group S envies group T. So this is good, but there is a slight problem here. We have not talked about the size of the group S and the size of the group T. Right? Certainly, if a group of 2 agents looks towards another group of 10 agents, the group of 10 agents might be allocated a whole lot more resources than this group of 2 agents. And so this group of 2 agents might envy the group of 10 agents, but that's kind of valid, right? Because the more agents you have, the more you are going to allocate. So what we do is we scale the utilities to this members in S by a factor that is size of S divided by size of T before checking if this is actually an improvement for them. Okay? So formally, we look at all possible pairs of groups, S and T, and we get all possible ways in which the group S can look at the total, the union of resources allocated to members of T, redivide it amongst themselves in some fashion, and then for each member in S, we look at the utility under this new allocation, but then we scale it by a factor which is the size of the group S divided by size of group T. So if S contains 2 members and T contains 10 members, then we are going to divide this utility by a 5, and then we are going to check if this Pareto dominates their original utilities. So I don't want to dive too deep into this section because this and its relaxations that I'm going to consider are very intricate. But this is not an up-to-one good set, is that this notion actually is one of the strongest notions that have been proposed in the literature. In particular, it implies a bunch of other fairness and efficiency notions that people have looked at, including ambiguous and Pareto optimality. And because group fairness implies ambiguity,
your connection is a little.
When your goods are,
Your
got a message saying that my connection is unstable.
Yes.
Is it any better now?
No, yes. We lost like the last 1 minute, I guess.
Okay. So maybe I'll just start from here again.
Okay.
All right. So this group-wise fairness notion basically says that if you take any pair of groups S and T, and if you look at any way of allocating the resources that are given to members of T amongst members of S, you take the utility to each member in S under this new allocation, but then you scale it by the size of S divided by size of T. So for example, if S has 2 members and T has 10 members, then you divide this new utility by 5, right? 2 divided by 10, that's 1/5. And then you check whether this new utility is 2 members in S Pareto dominate the old utilities that they had under the current allocation. And if this still Pareto dominates, then we say that group fairness is violated for these two groups. And note that this group fairness is not an up-to-one good style relaxation, it's an exact notion of fairness. In particular, it is one of the strongest notions of fairness that has been looked at in the literature. It implies a bunch of other fairness and efficiency notions that people have studied. And in particular, it implies both ambiguous and because we already know even ambiguity, the definition of this because it's a bit technically involved. But with a few collaborators back in 2019, what we showed, if you just maximize this NASH welfare function, this not only satisfies individual level fairness and fairness up to one good, it also satisfies group level fairness. So it actually satisfies group fairness up to one good, in addition to satisfying Pareto optimality. And note that, but this maximum NASH welfare rule is NP hard to compute. So what we show is that if you are willing to sacrifice Pareto optimality, then just compute a local optimum of this NASH welfare function, which you can actually do in pseudo polynomial time, and this is enough to get group fairness up to one good. All right. There are a bunch of other open questions here as well. For example, can you compute a local optimum of this NASH welfare function, or otherwise any group fair allocation up to one good in polynomial time? So this is a question that's wide open at this moment. All right. So just to summarize what we saw so far, we initially looked at this maximum NASH welfare rule. We showed that this is NV-free up to one good and Pareto optimal, so fair and efficient. Then we noticed that this individual level fairness is not good enough. We need to bump it up to a group level fairness notion. But it turns out that maximizing NASH welfare already satisfies this group level fairness notion. And at this point, my collaborators and I started wondering if this is fair enough. Okay? Is this good enough, or do we even need to get better fairness guarantees? And the answer is that this is not fair enough. And to see why, let us go back to this very simple example, where you have 3 people, and now you have 4 identical candies to divide between them. So what can you do? Well, if you have 4 candies, the only reasonable thing to do is to give 2 candies to one of the 3 people, and the other 2 people would get a single candy each. It's a bit unfair, but really this is the most fair thing that you can do, and somebody has to get 2 candies. But the question is, how do you decide who gets 2 candies? If you decide this deterministically without flipping any coins, then you are introducing some bias into the system. And indeed, if you go to split it and you try this instance on split it, where you create a dummy instance involving 3 agents, Alice, Bob, and Claire, and you put 4 identical candies as resources, then it turns out that split it always seems to break ties in favor of the agent who is listed first in the ordering. Okay, so if you list Alice first, then Alice will always get 2 candies no matter how many times you create this instance and run the allocation procedure. And this is a bit unfair. Of course, this problem wouldn't arise if these goods were divisible, if you can actually break the goods and divide between 3 people, because then you could give each person a full candy and then split the 4th candy and give a third of it to each person. Now, it turns out that if you are allowed to use randomization, if you are allowed to flip coins and introduce some randomness, then you can kind of mimic this allocation. What you can make sure is that each person receives exactly 1 1/3 candies in expectation. And that would be fair in expectation to the 3 individuals. However, this is not good enough. Okay, if you just want to achieve 1 1/3 candies to each agent in expectation, you can do a very bad randomization where you just select an agent at random and give them all the 4 candies. Certainly, in expectation, things are fair. Okay, in expectation, each person is receiving the same number of candies. So while things are fair ex ante, or in expectation before the coins are tossed, things aren't fair ex post, that is after the coins are tossed. Okay, after the coins are tossed, it violates all of the fairness notions that you can think of, for example, envy freeness up to 1 good. All right. So, of course, in this simple instance, there is a good way to answer this. You can get both fairness ex ante and fairness ex post by just choosing an agent at random and giving them 2 candies, while giving the other 2 agents a single candy each. And this would be the right way of doing the randomization in this particular example, and it would be fair both before the coins are tossed and after the coins are tossed. But the question is, how do we achieve this more generally? So this was a very simple instance. Can we always achieve fairness ex ante in expectation by only randomizing over allocations that are also fair ex post? And can we do that when agents have different valuations over the goods and the goods are not identical? So in this very recent work, my collaborators and I looked at a bunch of different fairness notions that can be guaranteed ex ante and ex post. And I'm not going to go over all of these notions and their acronyms, but I just want to show this one graph, which is the graph that depicts all of these different fairness guarantees. And whenever I draw an edge from one node to another node, that means that this fairness guarantee actually implies this fairness guarantee. So for example, if you get group fairness in expectation, it implies that you also have envy freeness in expectation. So the most interesting positive result that we have in this work is this positive result, which says that you can get ex post envy freeness up to 1 good and ex ante envy freeness at the same time. So you can take envy free up to 1 good allocations, and just by randomizing over these allocations in a smart way, you can eliminate any envy that agents have towards other agents in expectation. Okay, so this is great, although this requires very different techniques than what I've shown you so far. For example, we also show that this maximum Nash welfare rule is very much not amenable to adding randomness. Okay, so you need a very different procedure in order to get these 2 properties at the same time. The question is, can we make this a bit stronger? So for example, what if we add some efficiency guarantee like Pareto optimality? So instead of asking if you can randomize over EF1 allocations to get envy freeness in expectation, can we randomize over allocations that are both EF1 and Pareto optimal, the kind of allocations that are returned by this maximum Nash welfare rule? Can we randomize over those allocations and get this envy freeness in expectation? This actually is still an open question, and it's one of the most important open questions from this work. It remains unknown even if we relax envy freeness to something weaker called proportionality. But if you then strengthen this Pareto optimality guarantee to something called fractional Pareto optimality, which is a bit stronger, then we show an impossibility result. So again, I don't want to dive into the definitions of all these different notions, but the key message here is that if you want to get ex post NP-freeness up to one good, then this is very restrictive. There are certain things that you cannot achieve in addition to that. But if you are willing to relax ex post NP-freeness up to one good to two different relaxations, then you can actually get both of them along with the strongest property on the other side, which is group fairness in expectation. We also have some other results in this work, so if you're interested, you can check it out. For example, we characterize this maximum Nash welfare rule when, in the case when the goods are divisible, and we also extend all these results to the allocation of chores rather than goods. So these are items that people hate rather than love, and they have this utility for receiving these items rather than a utility for receiving them. It turns out that some of the results extend easily to the case of chores, but some results do not extend easily to the case of chores. All right, and there are some open questions in this line of work as well. So in addition to the open questions that I mentioned in the previous slide, you can also look at some other combinations and ask whether they are achievable, or you can also extend this type of analysis to other frameworks other than just resource allocation, things like voting or matching. All right, so until now, I talked about different levels of fairness that you can achieve and how you can achieve better and better levels of fairness along with some efficiency guarantees. But I did not talk about incentives at all. And as I had promised at the very beginning of the talk, I am going to look at incentives, but only now towards the end of my talk. And the reason for that is very simple. Incentives are very difficult to achieve in this domain of allocating resources to individuals. So the question that we want to ask is, what if you design a rule, let's say the maximum Nash welfare rule, and after you deploy this rule on some platform, the agents figure out that they actually can misreport their valuations in order to benefit from the rule. So instead of reporting my correct valuation over the different items, maybe I can lie about what my value is for the different items. And by doing so, the algorithm would allocate me a different set of items that I actually value more than the items that I would have received if I had told the truth. So the literature on game theory offers a very compelling axiom that if your mechanism satisfies it, then it would not be susceptible to such manipulations. So this axiom is called strategy proofness, and at a high level it says something like this. It says that no individual should be able to benefit by misreporting their valuations regardless of what the other agents are doing, regardless of whether the other agents are telling the truth or whether they are lying. So in other words, if you fix the reports of all the other agents, and then if an individual I receives a bundle AI when she tells the truth VI, and she gets some AI prime when she lies about her valuation function and reports a VI prime instead, then her value VI for the bundle that she receives under honest reporting AI should be at least as much as her value, her true value VI, of the bundle that she would receive by lying AI prime. And this holds regardless of what the other agents are submitting. So Klaus and Miyagawa in 2001 showed a pretty negative results. They showed that if you have even just two agents, even with that, it is already impossible to get strategy proofness and Pareto optimality, so this incentive property and efficiency at the same time, unless you are running a serial dictatorship, which basically means that the first agent comes to the table, takes all the items that they have any positive value for, only leaving behind the items that they have zero value for, and only then the second agents and the third agents, they get their share. Okay. So this proof relies on allowing each agent to have at least 3 different values for the items. So one question that we very recently asked with our collaborators is, what happens if an agent can only have 2 different values for a given item? So let's look at a very simple case where an agent can either like an item and have value 1 for it, or dislike an item and have value 0 for it. What we show is that in this very limited world, you can actually get incentives, fairness, and efficiency at the same time. So you can just have this rule that maximizes NASH welfare. You can add in some, you need to add in some lexicographic tie-breaking rule that I won't go into. And this not only gets you the envy-freeness up to one good and Pareto optimality notions that I talked about before, it also gets you strategicness in addition to that. Okay? And moreover, it no longer is NP hard to compute. You can actually compute this in polynomial time. And in fact, now you can also add randomization on top of that, and you can get ex ante group fairness, which in turn implies ex ante envy-freeness without losing any of the exposed properties that you have. Okay, so you can get basically all the properties that you want just by this one rule. Okay, but this only works in this limited settings when agents can either like or dislike a good and not in a more general setting. By the way, in fact, this rule is not only resistant to manipulations by individual agents, even if a group of agents decide to simultaneously misreport their valuations, this would also be resistant to that. All right, so that ends the technical part of my talk. Before concluding, I just want to point out a few future challenges. So one is obviously to get better and better fairness notions, or to extend these notions to domains of resource allocation where people's valuations are not additive over the items. For example, if you get, if your value for the left and the right shoe combined might be certainly way higher than your value for each individual shoe added together. You can also look at allocation of chores or bets. You can also look at some constraints on the allocations that come from the real world. For example, that all the agents must receive exactly the same number of items. But more broadly, fairness is very less understood, even in this domain. All the notions that I talked about are very static, right? So this is one-shot resource allocation. But if you have agents who interact with the system over time, and they are being given some resources over time, how do you extend these notions to that? Or what if you have to take agents' merit into account? What if some agents deserve to get more out of the system than some other agents? For example, in shared economies, where different agents contribute different amounts of money, it is reasonable to ask that agents who contribute more money into the system deserve to get more resources out of the system. You can also look at incentives, and I talked about this very recent work where we start looking at incentives, but this is still relatively less explored than in other aspects of computational economics. Recently, this has been explored in machine learning as well, so I have some joint work with my students and my collaborators on looking at strategic manipulations in machine learning algorithms. And more broadly, things like ethics aren't even well defined. While we have formal definitions of what it means to be fair, efficient, and resistant to incentives or manipulations, we don't even know formally what it means to be ethical. And there are different notions out there, but nothing very compelling. And while an axiomatic work has certain dangers involved, for example, these axioms are only worst case, right? Even though it may be very difficult to get both envy-freeness and Pareto optimality at the same time on every single instance by the same rule, on certain instances, these axioms might be very relaxed. So you don't just want to output an arbitrary solution that satisfies a certain axioms, you want to output a solution that inherently makes sense. But nonetheless, these axioms are helpful for other purposes, like explainability. So on split, for example, we use these notions of envy-freeness up to one good and Pareto optimality to explain to the users why the allocation that is given to them is fair. So we explain to them that, look, according to the points that you assign to the different items, you don't envy these agents, and why do you envy these other agents? You wouldn't have envied them if you ignored this one good in their bundle. And these are the four references, the four papers that I talked about in this talk. And I just want to conclude by giving a shout out to another not-for-profit website that my collaborators and I have founded called RoboVote. So unlike Split, which is about resource allocation, this is about voting. And you can vote about things that are about subjective preferences, like where you want to go for lunch, or you can vote about things that are objective in some sense, like who is going to win the 2020 US presidential election, right? Where different peoples might have different noisy opinions, and you might want to agree with these opinions to recover the ground truth. Okay, that's it. Thank you, and I can now take questions.
Thank you. We have a lot of questions, but I think we don't have the time to answer them all. So I'll choose some. We'll start with Francisco Veron question, which is, have you worked with machine learning in this topic? And if so, do you think these algorithms can be used to get rid of some of the biases that we see in machine learning?
Yeah, so certainly one of my recent areas of interest have been machine learning and looking at how to achieve better fairness properties and make them more resistant to manipulations. And so I have some recent work that looks at fairness notions that come from. Sorry.
The connection got a little unstable when you were.
Oh, the connection was again. Okay.
Yeah, okay. Now it's back on.
Now. Okay. Okay. Perfect. Yeah. So recently, I think I'm again getting the connection unstable warning. All right. I'll just continue nonetheless. So I have worked with some students and some collaborators recently on converting these kind of fairness notions that we look at in fair resource allocation into machine learning work, right? So looking at how do we design envy-free classifiers, for example, in machine learning, or group fair classifiers in machine learning. And so there is a long way to go in this line of work. I mean, this is really just at the technical stage right now. There is a long way to go in understanding what people really treat as fair and unfair, right? So these are definitions that have been proposed in the literature by researchers. We have no idea whether real humans, whether they find these definitions fair. So there is a long way to go in understanding what fairness means in machine learning and how to achieve it. But I do believe that these preference-based fairness notions, which look at the preferences of the individuals which are being affected by the outcomes of these machine learning algorithms, have real applications in machine learning literature, where the current notions do not look at preferences. They look at things like false positive rate and false negative rate, etc.
Okay, so I'm gonna ask the next question. Does the efficiency of current computational implementations of those strategies prevent their application to wider social issues with much larger number of agents?
Yeah, so this is certainly true. So for example, on Splendid, we have deployed this maximum NASH welfare rule, which I mentioned is strongly NP hard to compute. So we have developed some efficient heuristics for computing this rule exactly. And these heuristics certainly don't run in polynomial time, but they run reasonably well. So if you have, say, if you are trying to divide an inheritance of like 200 items among 10 people, you can solve this within a minute. But if you have much larger numbers of items or agents involved in a particular instance, then you would not be able to scale these techniques. So there is also some interesting research going on right now for designing near linear time algorithms or really fast algorithms for solving these kind of allocation problems.
Okay. Next, and I think the final one because of the time. In your presentation, it's assumed that every agent knows how much each item values, but it's not exactly what happens every time. How to deal with those kind of noises?
That's a really great question, because very often once people kind of report their valuations and then they see the final allocation returned by Splendid, then they email us complaining that, you know what, I should have put more value on the car. Now that I lost the car, I realized that I probably didn't value it as much as I wanted, and the items that I received are worthless, and please let me change my valuation again. So people don't often know exactly how much cardinal value they put on the different items, they should put on the different items. And so there are two ways of addressing this. One way is where we don't ask them for their values for the different items upfront. Rather, we do something like this. So we show them a partition of the bundles, right? So we partition the items into n bundles, and then we ask them, if this is how we had partitioned the items into the different bundles, which bundle would you have wanted, right? And each person picks a bundle that they want. If two people pick the same bundle, then we are in a conflict. We can't really allocate the bundles to the agents yet. So we then repartition the items into different bundles, right? And then we again ask the agents to pick the bundle that they like the most. And at some point, if we reach a point where each person picks a different bundle, then we know that the allocation is going to be envy-free. And since people are only comparing bundles, this kind of elicitation is more resistant to this kind of noise. The other approach is to directly ask them for their cardinal valuations, but to explicitly know that people's valuations are not going to be accurate. People are going to make mistakes when they submit these valuations. And so what you would want is some kind of guarantee that fairness would hold approximately, even if there is some little amount of noise in the valuations, right? And so there is a very recent work that came out of two researchers from University of Waterloo that started looking at design of stable fair division algorithms. So the stability is in the sense that if the agents make just very, very small mistakes in giving the valuations, this shouldn't fundamentally change how the allocation procedure works. Okay, so a small change in the valuations should only imply a small change in the final output. And so this again is a very open field. I mean, this paper that I mentioned is the first paper that I know along these lines. So there is a lot of work that remains to be done.
Okay, so that I think thank you for the excellent talk. A lot of people liked it.
Thank you for inviting me. This was a great venue, and I love being here.
Some people are asking if you could make your slides available.
Oh, yeah, certainly. I can send you my slides, and you can make them available through the web page.
Great.
Sounds good. All right. Thank you, everyone, for having me. And bon appetit.
Thank you. Okay. Now we're going to take a break for lunch. And next, but before the break, there is a testimony of a former student of ours about the experience in the course. Thank you again, Nisarg, and thank you all for watching.
Bye-bye.